Alright, so we're talking about our theoretical building blocks around the z, t, and c squared statistics. So last time we already talked about the z statistic. Now let's talk about the c squared first. Okay, so this is a repeat in the last chapter. Remember we talked about the chi-square distribution. So let's remember that it is a function of random variables, which are normal 0, 1. They are squared, and we add them up, and there's r of them. Okay, it turns out that this sum has this distribution, chi-square distribution, and we're going to look up the values of the probabilities in the chi-square table right here. Okay, and another important property is that the sum of two chi-squares is also chi-square with the sum of the degrees of freedom, right? Okay. Now, it turns out that this statistic, c squared defined like this, has the chi-square distribution with n minus 1 degrees of freedom. N minus 1 is the sample size minus 1, right? Okay. Now, to see why this is true, please follow this proof. We're not going to do it. I'm just going to run quickly with it. Okay, so first line, that's the definition of n minus 1 times s squared. Okay? Remember the definition of s squared? It's the same thing. Alright, we add and subtract mu, and then we use kind of a shortcut formula for this expression right here. Okay, so you have the first term squared minus n times x bar minus mu. So it's really similar to the shortcut formula for s squared. If you compare with it. Okay, dividing through by sigma squared, we get these two things. And this is the key here, right? Because it turns out that this is going to be chi-square with n degrees of freedom, and this is chi-square with 1 degree of freedom. Now, why is that? So, pay close attention. So, here, xi minus mu divided by sigma has to be a normal 0, 1 distribution because all the xi's, remember, are assumed to be IID. Sorry about that. Normal mu sigma squared. Right, so this is the z-score of xi, right? So it's a normal 0, 1 that is being squared and added up. N of them. So that has to be chi-square n. And this term, remember, x bar, by now we know this, right, is normal mu and sigma squared divided by n. That's the difference. Okay? But here it's also normal 0, 1, right? That's the z statistic we just defined. So squared, it's the chi-square of 1, right? Because you're adding up just 1. And then from this, you can say that therefore this guy has to be a chi-square of n minus 1 degrees of freedom. Right? Yeah. Okay, now a very important result that we're not going to prove. It's in the book if you want to look at the proof, because it's so important. But we're just going to state it. And it's the fact that x bar and s squared are independent, which is not at all intuitive, right? Because x bar and x squared are calculated from the same sample, right? It's formulas, right? The formulas in the first slide on this chapter, they use the same sample, right? So you might expect that if one changes, the other one will have to change. Well, they do change, right? But in a way that it's not that they're independent, okay? And independence is going to be important to define the t statistics in the next slide, okay? So again, please go to the book if you're interested in the intuition for the proof, because yeah, it's really not intuitive. All right, but x bar and s squared turn out to be independent. All right, and that's why we can define the t statistic in this way. Right, so again, this is comes from chapter 5, the end of chapter 5. So t is the function of two random variables, u and v, in this way, right? So again, please go to that chapter to see the details. And again, we're going to use the t distribution tables in a minute to obtain the values. Or of course, you can use your calculators. Okay, so that's the definition of a t distribution, right? Now, why is this relevant to us? Okay, it's because remember when we said up here for the z statistic that when we don't know sigma, we replace it by s, but then we have to use the t distribution, right? So if you compare the t and the z, so for the t, here we're just going to put s, and we're going to call it t. Really, that's all we're done. And it's no longer n minus 1, it's going to be t distribution with n minus 1 degrees of freedom. Minus. Alright, so that's the change we make, which is this equation right here, right? Okay, so that's our t distribution, very important. So again, same as z, but using sigma, using s instead of sigma, and that's a big deal. Alright, so the proof, why is this t distributed, is like this, right? So we know that z and c squared are defined in this way. Okay? And then it turns out that the t distribution can also be expressed in this way. So please try to replace the definitions of z squared, z and c squared, and you will see that you obtain the same. And since they're independent, this is where the independence part is important. Since x bar and s squared are independent, then this would be the ratio as such in the definition, right, of a normal random variable in the numerator and a chi-square distribution, chi-square random variable in the denominator with the square root and the degrees of freedom, right, which is what we have here. Okay? So that's why it corresponds to the t distribution. Right, so what we're saying is basically that this formula right here, you can also express it as z, right, divided by the square root of c squared divided by the degrees of freedom, which would be n minus 1. So these two are the same. Right, just replace the definitions of z and c squared up here, and then you'll see that you obtain this one. Okay? And this guy is the definition of a t distribution, right? It's a normal 0, 1 divided by a chi-square. And they're independent. Alright. So that's it. These are the building blocks of statistics. And it turns out of these three statistics, we're going to do everything we need. Alright, let's talk about estimators. So an estimator is going to be a function of random variables. That's why we had chapter 5, right? So let's give the name theta for an estimator. So theta could be either mu or sigma squared, right? It's your generic parameter that you want to estimate. And then we're going to put a hat on top for, that's going to be, the hat's going to mean estimator. So theta hat is going to be an estimator of theta. So examples of theta hat that we've seen before, it's x bar and s squared, right? Those are theta hats for mu and for sigma squared. Okay, so as you saw before, x bar and s squared are formulas of the random sample. So they're functions of random variables, really. That's the best way to visualize what an estimator is. right? Like x bar, right, is this average 1 over n sum of xi. So that's your function. Takes the sum of all those and divided by n. All right. So estimators are functions only of the observed data, not of other unknown parameters, and it is itself a random variable. Okay. And this might cause some confusion. So we said that theta, like that, without the hat, is a parameter, not a random variable. But the theta hat is a random variable, right? Because it's a function of random variables. Okay? And this means random variables, not Rn, I guess. Okay. And we're going to define three properties, or good properties, or desirable properties of estimators. First is unbiasedness. We defined it before, so if you take the expected value of the estimator, you recover the original estimate. So we did it last time with mu, with x bar, and we showed that the expected value of x bar is mu, as required. Below, we're going to show that the expected value of x squared is in fact sigma squared. And actually, that's why for s squared, and this is s squared, not delta, that's why we have to divide by n minus 1, the s squared. Because otherwise, it's not going to be unbiased. Okay? So that's why we say that these are the best estimators, because they're unbiased. Now there are others that may be good as well. All right, but unbiasedness is not the only thing you look for an estimator. You also want it to be consistent. All right, so consistency means that as the sample size goes to infinity, so as it grows, then your estimator tends to the true parameter. Okay? So it says the sample size grows, it tends to the true parameter. Now, we know that this is true for x bar, right? Because of the large numbers, right? Since the variance of x bar, remember, the variance of x bar is sigma squared divided by n. As n goes to infinity, then the variance of x bar goes to 0, meaning that x bar will tend to the true value of mu. So that's a consistent estimator. All right, and the other one is efficiency. So if you have to choose between two estimators for the same parameter, you're going to choose the one with the smallest variance. That's what efficiency means, okay? So these are just indications or guidelines how to choose a good estimator. So basically you want it to be unbiased. That's number one. And then hopefully they'll be consistent and efficient. All right. So here we're going to show that s squared is unbiased. So we've seen this already. That's good. Now for unbiasedness of s squared, remember, so s squared comes from here, right? That's the definition of s squared. We just multiply by n minus 1 to make it more readable. But it's, yeah, that's what s squared is. All right, so again, we subtract and add mu. And then this is the shortcut formula for that. So sum of this squared minus n times this squared. Okay, so that's, we're good up to there. And next step, we're going to take expected values of that, right? To make sure it's unbiased. And when you do, so let's just put in expected values everywhere. And here we, the expected value comes in summations, and then you identify that that is the variance of x by definition, which is sigma squared. And same thing here, that's the variance of x bar, right? X bar minus its mean squared the expected value of that is the variance of x bar, which is sigma squared divided by n, and therefore it simplifies to that. So you see from here that S squared, it is unbiased, right? Because this is the definition of unbiasedness, right? And that explains why we need to divide by n minus 1 and not by n when we do the formula for S squared, right? Remember, S squared is 1 over n minus 1 summation, etc. So that's why we use n minus 1. Because in this way, it's going to be unbiased. Now, in practice, typically these days when we have so much data, the difference of dividing by a million or a million minus 1 is not important at all, right? So this difference is also always only important for small sample size. All right, so up to that point, we discussed the theory. Now we're going to do the applications of this theory. So we're going to do confidence intervals first, and then we're going to do hypothesis testing, and we'll call it a chapter. Very good. Okay. So confidence intervals is a random interval, in this case with limits a x and b of x, that contain a parameter with certain probability. Okay? And again, remember, here's really important, the difference between capital and lowercase. Right, capital is random variable, lowercase is a realization, it's a number, so it's not a random variable anymore. Okay. Now, when the limits are a function of capital X's, this equation makes perfect sense. Right, it says that you're gonna find out these random variables a and b that would contain the true value of the parameter you're trying to estimate, like mu or sigma squared. Okay, and you want that parameter to be in this interval with this probability 1 minus alpha. All right, so 1 minus alpha is known as the confidence, 1 minus alpha is called the significance level. And we're going to talk in detail about it. Okay? Or confidence level, in this case, it's more appropriate. So, confidence. Okay, so you want that probability to be high. Typically it's 95%. So 1 minus alpha is 95%. Typically the default value for alpha is 5%. Okay, and alpha is called the significance level. And 1 minus alpha would be the confidence. Again, we're going to talk about alpha in more detail. Okay, so up to here, I'm good. The problem comes after that. The problem is that when we have a realization, right, with lowercase x, then what we say is that the interval a little x comma b little x is going to be your 1 minus alpha % confident interval for the parameter. Okay, now the part that I find problematic is that by going from uppercase to lowercase interval, we lose the interpretation that we would like to have, which was the original, right? Is that this interval contained the true parameter with this probability. Okay, but look, let me just write it down. When I write this down, so the same thing but with lowercase x. It's supposed to be lowercase x. Now, this statement no longer makes sense, and that's a problem. So this is wrong, and that's the wrong interpretation of confidence interval, right? Because here, what is the random variable in this? Anyone? I'm just kidding. Right? There's no random variable, and that's the problem, because little x is not a random variable anymore, it's a realization. So that you can't attach probabilities to a statement that doesn't have a random variable here. Remember, the parameter is a constant, is an unknown number, but it's not a random variable. So this is the wrong interpretation of confidence interval, and unfortunately that's the one that most people have. All right, so what is the right interpretation? And it's this one right here, which is not very useful, to be honest, in practice, and that's my problem with confidence intervals. So so to reiterate, my problem with confidence intervals is that we tend to interpret it in a way that is wrong, okay, and therefore they're not very useful, because the interpretation that you see here is not useful at all in practice, right? Because it says that you would have to repeat the experiment of computing these confidence intervals many times. So let's say you do it 1,000 times, right? And the experiment is collect a sample and compute these intervals, A and B. Okay? And then if you do it 1,000 times and you choose alpha to be 5%, then you would want to say that in 950 of those samples, those intervals will contain the true mean. But 5% of those intervals will not contain the true mean. Now, the problem is that you don't know which contain the true mean or not. So it's problematic. All right? So we're going to see the formulas. You know how to do it, because you have to know how to do it. That's one of the most typical uses of statistics. But please be careful about how to interpret it. Okay? All right. So let's see how we do this. Okay, so now we're going to define critical values. Z of alpha now, right? So alpha is this 5% significance level that we just defined. And again, it's default value 5% unless they tell you otherwise. Okay? All right, now the problem with critical values is that typically they're defined in this way, is the area to the right. So it would be a percentile, but it would be like the 1 minus alpha percentile. Right? So this is the best picture. Z of alpha is the value here, so in this case it's 1.645. So it's the value of Z in this case, such that the area to the right is alpha, 5% in this case. Yeah, because 1 minus alpha is 0.95, right? So, and we're going to call these the critical values. Okay, and notice by symmetry, because the normal distribution is symmetrical with respect to 0, that right here we're going to have Z of 1 minus alpha, so of 0.95, right? Because this area would be the same as this area. Alright, so those are the critical values. And these are the famous ones, right? 5% for alpha. So this one we just saw. And also alpha over 2 will be really important. right? 1.96, which is almost the number 2. All right, so we're going to use these values, all that. And this is where the alpha over 2 comes in, right? So here, we're going to start with the confidence interval for mu. Then we're going to do the 1/4 sigma squared. Okay? So, yeah, there's two-sided and one-sided intervals. So an interval here, let's start with the two-sided. Okay. Now, this is a statement that we said before, right? We want to construct an interval a and b that it contains the random variable 1 minus alpha % of the time. Okay, so in this case, these are the values of a and b. Well, the z alpha over 2, right? And you see that from the figure. So you have a random variable z, right? Now, by definition of percentiles, this statement is true right here, right? Because these two numbers, z of alpha over 2 and negative it, are such that the area, the yellow area is 0.95, and the other two are 2.5%. Right, so by definition, you must have that the probability that the random variable z falls within this yellow interval, let's say, is 95%. By definition of percentile, or critical value in this case. Okay, so this is by definition. Okay, so there's no problem with the statement because z is in capital letters, so there's a random variable, so no problem. The problem comes here. So the first line is the same. We're just replacing z by the definition of z, which is that, right? Okay, and then this is where we have the problem. No problem yet, because x bar is still on capital, right? So that's a random variable, no problem. And so what we did from this line to this line is just simply rearrange it so that mu is in the middle here, right? And from this equation, these two inequalities, you can deduce the interval for mu, right? So that's going to be your, remember your a of x term that we had before, and this would be your b of x term in the very first definition of confidence intervals. Okay, so these are the, a of x comma b of x. So that's the shape of these random intervals, all right? So no problem here. The problem is when you realize these intervals, right? So the way we realize them is by taking a sample, right? You see that in this formula right here, you have the random variable x bar, but all the rest are numbers that you know, right? Sigma, you're supposed to know it if you're going to use this formula. Z squared we already know is 1.96, and n is the sample size, right? So the only random variable is x bar, right? So to obtain a realization of this interval, we're going to take a sample, and then we're going to plug in the value of x bar that you obtain in the sample here, right? That's why they're lowercase. Okay, so in this equation up here, I can say that there's a 95% probability that mu would be in this interval, because this is a random variable, random interval. It's not a number. Okay? So here you can say, there's a 95% probability that the true value of mu would be in that interval. Now the problem is that you don't know the values of those, the limits of the interval. They're random variables. Now when you do, you take take a sample and compute a realization of the interval, then you're going to get two numbers, right? So let's say this is 1 and 3, just to say something. Okay, so the problem is that you cannot say that the true value of mu is between 1 and 3. You cannot say that. Now, the way people go around it is saying that this is the 95% confidence interval, and they leave it up to the listener to interpret that, right? Other thing people say would be, we can say with 95% confidence that the true value of mu would be between 1 and 3, which is kind of cheating if you don't know that confidence is not probability, right? Again, we say that up here you can say, yeah, there's a probability of 95%. But here, what people circumvent this is by saying the word confidence instead of probability. All right, so be careful with that difference. Yeah, so what is confidence? Confidence is a very confusing term, right? Because it's not the confidence you're used to. And it goes back to the true interpretation of intervals, okay? Right, so this is the wrong interpretation. And so if we repeat it over and over again, we would have the, right? So this percent of the intervals that you calculated will contain the true mean. And that's the definition, or not definition, but the concept of confidence, right? Is if you repeat it, the experiment 100 times, which you never do, right? We only do the experiment once. You collect one sample and compute one confidence interval. All right, so be careful with the word confidence. Very misleading. Very good. Okay, let's define the margin of error, or half-width. All right, so you see here that these intervals are symmetric, right? Because you can express it as x bar plus or minus something is the same something, right? And that's the half-width. This is what we call the half-width, h, right? Because it's x bar, so these intervals are centered at x bar. And the width of the interval is 2 times h, right? Or margin of error. Right? Because your interval is like that, right in the middle you have x bar, and then you have h in each side. Alright. And from here you could solve what's the sample size needed for a given or a prescribed margin of error. So if they ask you what's the sample size needed to estimate the wind speed within 3 miles per hour, then h would be 3 in that case, right? And the way you obtain the sample size is just solving for n in this equation, and that gives you the required n given h. Okay, so that's the way we're going to compute sample sizes. Now, notice that this equation needs the value of sigma, right? So up to here, we're assuming that we know sigma, which is not practical. In practice, we never know sigma, but this is just to get things started, okay? All right. Let's do a quick example here. So we have a sample of these numbers, right? And these are the time between arrivals of vehicles at a toll booth. All right, 1.2 seconds, 3 seconds, etc. Okay, sample mean and variance, that's easy. But then let's compute the 95% confidence interval. Okay, and here they say assume that sigma is given and equal to s squared. So sigma equals s here, just because they tell you, right? But in general, we don't know sigma. Okay, so for part B, it's just plugging in values here in the equation. We know everything because we computed x bar and sigma, or s, in part A. So there's no problem of computing this guy. And, well, I guess I will plug in the numbers in class, I guess, right? But you see, you know everything because that's 1.96. They don't tell you alpha, but you assume it to be 5%. Or maybe they did tell you. Oh yeah, 95%. That's also 1.95, sorry, 96. N is 1, 2, 3, 4, 5, 6, 7. That's supposed to be a number 7. Alright, so you're going to get two numbers. Okay, Okay, so this interval is from 2.8 to 7.3. Right. But the point is really useless. Because we cannot say anything with these two numbers, 2.8, 73, right? We would like to say that there's 95% probability that the true value of mu is within that interval, but we can't. All we can say is, if we repeated this 100 times, then 95% of those intervals would contain the true mean, right? Which is rather useless. What is not so useless is the margin of error. So that's, we call it h, right? The half width. So that gives you an indication, half, of course, of the width of the interval, but also of the variance, right? So because h is related to the variance sigma. So the half width is a measure, right, of sigma in this case. So it's a little more useful than the confidence intervals itself. Okay? And I got 2.3 for this one. All right, and then what is the sample size needed to reduce that margin of error by a factor of 2? Okay, so in here, the h that we're using is a factor of 2, so 2.3 divided by 2. 2.3 is what I mean here, right? So if you plug the number in, you get 28. Now, notice that 28 is 4 times 7, and 7 was our original sample size. So with 7 points, we obtain a margin of error of 2.3. But if we want to reduce that 2.3 just by a factor of 2, the sample size grows by a factor of 4. So 2 squared, right? Which is not good, right? It's the square that's here that's gonna, right? Because I could write this h. So let's say that h right there in the equation now, it's 2.3, so I would put divided by 2, right? So this divided by 2 here becomes the 4 that it's in here. Okay, so it's really expensive to reduce the margin of error in general because of this square. So we need to be careful there when computing sample size. Okay, let's go back to, now that we know how to compute intervals, let's go back to our interpretation of these guys. Okay, so I implemented this on a spreadsheet, and we're going to repeat the example we just did. So we take a sample of size n. So that's point number 1 there. Okay, and so in this case, the sample we're doing it in Excel, so we're simulating numbers from a normal mu equals 50. Okay, So in this case, because I'm simulating it, I know the true value of mu, but in real life we don't, okay? It's just to show the intuition. Okay, so we repeat this procedure 100 times, right? So first we take the sample, then we compute the confidence interval with the formulas we just did, and then we plot them next to each other. And this is what we obtain here. So that's 50, that's the true value of mu. So in this case, we're lucky to know it because then we can verify, right? So alpha is 5%, so you expect 5 intervals of these 100 not to contain the number 50. Okay, so here you have all the intervals, and actually 5 of them do not. Now, not by much, so that might be one, you see, that might be another, etc. So there's 5 of these intervals that don't contain the green line, and that's the interpretation of confidence intervals, right? But each individual interval doesn't tell you anything, and that's my problem with these guys. All right. So here we're going to replace sigma by S, which is what we do in practice all the time because sigma is not known, but S is. So we're going to repeat the same analysis, right? We start with the same. That's going to be now the t distribution. And this is okay because there's a random variable, right? This is okay too. Now, when you observe a realization is the problem. Now, notice it has exact same formulas as before, but instead of the critical value from the z distribution, we take it from the t distribution, right? And instead of sigma, we're going to use S. Okay, concept is the same. The only difference is that we need to compute these guys because these critical values depend on the sample size. Okay, and we're going to see how we do that in a minute. But again, same problem of interpretation. Okay. So we also have 2 other types of intervals. So this is the two-sided interval, right, with upper and lower bound. Also, we have one-sided intervals, right? And so it's to obtain just a lower bound or an upper bound. So, for example, this would be the upper bound, right? Because it's x bar plus the half width. Remember we called this the half width before? Or margin of error. So that's your upper bound, and this guy is your lower bound, right? Okay, so these 2 numbers define these intervals. So for the lower bound, it's confusing because the lower confidence interval includes the upper bound, okay? But that's okay. Now, the other important difference is that instead of T alpha over 2 in these formulas, we always use T of alpha. Okay, and why is this? Because, so that's your T distribution, again, symmetric with respect to 0. When you're doing one-sided, it's like you're putting everything in one side. And by everything, I mean alpha, right? And all the rest is going to be 1 minus alpha and all the way up to positive infinity in this case, right? But before, remember this picture, we did the 2 tails, like here, right? We're putting alpha over 2, so these 2 red areas are both alpha over 2. Added up, they give you alpha, right? That's the 2-sided intervals. For one-sided, we're just going to put the whole alpha in one side. Okay, and that's why, so this is going to be then your negative T of alpha. Right, it's because we put it on one side. So this would be corresponding to this case and the opposite figure. So when you put alpha all in the right tail, that's T of alpha. This figure corresponds to this side, okay? But basically same formula and same problems of interpretation. Okay, so this is the same example we did before, but now we're not going to make the assumption that sigma is unknown, and we're just going to use S from the beginning. So the only difference will be the use of the critical values here, T instead of the Z distribution. All right, so let's see how we compute this value from the table. If you click on the link where we discuss the T distribution, this is what you get. All right, so it's the T table we're going to use. The degrees of freedom is the first column here. So you see n minus 1 is the degrees of freedom, so 6. Okay, so we're looking at column row 6. And then alpha is 5%, right? So we need to look here in the two tails area because it's a two-sided test, and the total area is alpha 0.5. Right, so the value is going to be 2.447. Okay, so that's 2.447. All right, and with these, that's the only difference with the other problem. Here I get from 2.2 to 7.9. So it's wider than the other interval because the t values, the critical values are larger. For this one, I get 2.86, again, larger half width than the normal. Okay, now for the sample size, we need to discuss this in more detail, but the problem is that T of alpha over 2 really is a function of n. Alpha over 2, we haven't said it explicitly, right? But when we say with degrees, n minus 1 degrees of freedom, that's where the n comes in. So really you have an implicit equation because you have n in this side and also in this side, right? And these equations, called implicit equations, are best solved by trial and error. So you need to try different numbers for n and see where, for what value of n, the left-hand side of this equation, so n, equals the right-hand side of this equation, which is that. Okay? So I did that in Excel, and I got n equals 20. All right? Now, this is something I won't ask on a test, but it could be on a homework. All right. See you guys in class.